you see at the top is, again, one of these locus. It's a collection of points. And this definition is just a little bit different than the previous ones. So we're going to start again with a sketch. It could be anywhere in the XY plane. We're just going to center ours at the origin to make life a little bit easier. So a hyperbola is a set of points in the plane. And then the key word here is the difference of whose distances from two distinct fixed points, called foci, is a positive constant. So we're going to start with a center, just like we did with an ellipse. The center is not part of the hyperbola, but it is part of that building. And your foci are going to be either both on the x-axis or parallel to the x-axis, or they could go up and down as well. When you're measuring your distances here, well, maybe I should sketch in the hyperbola first. It's kind of like you have two parabolas. So we'll say vertex 1 goes here, and it's going to open towards the focus. And vertex 2 would be a nice mirror image to the other side, opening and swallowing up the second focus. So it looks something like that. The distances that they're talking about in the definition, if you were to measure the length from focus 1 to any point on your hyperbola, we'll call that distance 1. And then if you were to measure from that point, again, but this time all the way to the second focus, we'll call that distance 2. The absolute value of distance 1 minus distance 2, so the other order doesn't matter, it's going to be equal to a constant. In the ellipse, it's their sum that's a constant. Here, it's the difference between them. So you could measure them, find the difference between, and then that would give you the set of points that makes your hyperbola. We talk about the graph having two disconnected branches, not rocks, branches. And the line segment that connects the vertices going through the foci is what we call the transverse axis. So imagine that there was an imaginary line here. It's your line of symmetry between focus to focus, up to down in this picture. And the midpoint of your transverse axis is called the center. So that's our general picture. The standard equation for a hyperbola, just like before, there are two of them, and it depends on your directions. So hyperbolas either open right, left, or up, down. Right, so my picture here is opening right to left. That equation would look something like this. Notice that if you're opening right and left, we'll make a little sketch next to it. Right? This would have your branches opening right and left. If you're opening right and left, your x is coming first. Always subtraction, always equal to 1. Your center is your h and k. So I'm going to make a little note here. This is the version you use when your transverse axis is horizontal. So the drawing I did at the top would look something like this, but the hk would be 0, 0. If you wanted your hyperbola to open up and down, then you would want to lead off with the y. And your general form would look like this. So whatever one is positive, right? The coefficient on the x squared term, the coefficient on the y squared term, those are the positives because here you're subtracting the y or subtracting the x. The transverse axis is the one that's leading. So here we're going to write transverse axis is vertical. And then the other thing to note that's very different than an ellipse, the A is always associated with the first term. So the A value is always associated with the transverse axis, and A does not need to be the biggest value. That's different than the ellipse. So I'm going to make a note here. The magnitude of A or B does not determine the transverse axis. It's the square term that would have the positive coefficient. We're going to write A goes with the positive, oops, I'm going to run out of space, positive squared term. And then I don't want it to get lost, but right underneath, the vertices are A units from the center. So if I wanted to add that to my picture here, from the center to a vertex would be A in both directions. B doesn't show up on our graph, but I will show you how to use it when we get to graphing from that standard form. And our foci, I don't want it to get lost here. It kind of got cut off by the page. But your C value is the distance from the center to the focus. Now notice here, unlike ellipses, right, the C value is bigger than the A value. And the relation, C squared equals A squared plus B squared. Looks like Pythagorean theorem, right? You can always remember because in the hyperbola, the focus is inside of the hyperbola, so it's got to be that C is larger than A. And so you have to add to make A squared get larger than C squared, unlike your ellipse where you're subtracting because your focus is coming before the edge of the ellipse. All right, we'll move into the examples in just a minute.